The air raid siren begins its mournful wail across Cologne at midnight on May 30th, 1942. Searchlights stab upward through the darkness, illuminating the night sky with an almost theatrical intensity. The German air defense crews scramble to their posts, knowing what is coming. 1,000 British bombers are inbound. But tonight is different. Tonight, something is about to happen that will transform the very nature of aerial bombardment, something that will leave the German Reich scrambling to respond to an enemy they cannot see, cannot hear, and cannot stop once it has been released. It will take hours, it will take days, it will take weeks. The bombs are falling, yes, but not all of them will explode when they strike. Some will wait, some will lie silent in the rubble, ticking quietly like watchmakers' creations, biding their time in the darkness beneath the streets of German cities, and when they finally do detonate, they will not detonate to the sound of impact or the flash of chemical reaction, but rather to the patient, inexorable turning of a clockwork mechanism. The delayed action bomb, a weapon so simple in concept, yet so devastatingly effective in execution, would become one of the most psychologically destabilizing innovations of the entire war. A piece of engineering that made victory not about the tonnage of explosives dropped, but about the uncertainty of when those explosives would finally release their terrible energy. This is the story of how Britain learned to harness time itself as a weapon. For the first 3 years of the Second World War, British bombing strategy had relied upon a fundamentally flawed assumption that conventional bombs would behave as expected. Drop a bomb on a building and it would explode on impact, creating a crater, collapsing structures, and causing immediate casualties. The Germans, operating under the same assumption, organized their air defense accordingly. Anti-aircraft crews could track incoming bombers and engage them in flight. Firefighters and rescue workers could move into bombed areas within hours of a raid, extinguishing fires and pulling survivors from the rubble. Repair crews could assess damage and begin rebuilding within days. German society, resilient and militarized as it was, could absorb these blows and recover. By 1941, despite months of bombing, German industrial production had actually increased. Factories damaged one week were operational again the next. Cities suffered, yes, but they endured. The RAF was learning a bitter lesson. Bombing alone, under existing conditions, could not break the enemy's will or capacity to wage war. The problem was not the weight of the bombs themselves, nor their destructive power. The problem was time. German civil defense had evolved into a finely tuned machine. Within hours of a bombing raid, the casualty figures were known. Within a day, rescue operations were underway. Within a week, repair gangs had cleared the rubble and begun reconstruction. The Germans had learned to compartmentalize their suffering. Entire neighborhoods could be sacrificed if the industrial infrastructure remained intact. This was a calculus that favored the defender far more than the attacker. Britain was expending enormous resources, fuel, aircraft, trained crews, to bomb Germany into submission, yet the German war economy continued to function, continued to produce tanks and aircraft and ammunition. Something fundamental needed to change. The technology was there. The bombers could reach German cities. The pilots were brave and well-trained. But the weapon itself, the bomb, was failing to achieve what political and military leaders demanded of it. By 1940, engineers working at various research facilities across Britain began experimenting with a radical concept. What if the bomb did not explode when it hit? What if, instead, it waited? What if it lay dormant in the rubble, silent and invisible, and only detonated hours or even days later, after rescue workers had gathered, after the immediate crisis had passed, after German resources had been mobilized for repair and recovery? Such a weapon would not merely cause destruction at the moment of impact. It would cause ongoing disruption. It would paralyze civil defense operations. It would force the Germans to assume that every piece of rubble might contain an unexploded bomb waiting to erupt. It would inject chaos into the most carefully organized rescue operations. And because the detonation would be delayed, it would cause secondary casualties, emergency workers, not civilians huddled in shelters. The engineering challenge was substantial but not insurmountable. The solution lay in the fuse, that small but critical component responsible for initiating the bomb's detonating sequence. Instead of the mechanical impact fuse that caused instantaneous detonation, designers needed to create a mechanism that could delay the explosion by a predetermined interval. Several approaches were explored in parallel. At the English Electric facilities in Coventry and at other manufacturing plants scattered across Britain, teams of engineers and technicians began developing what became known as the Type 17 and Type 47 fuses, mechanical clockwork devices of extraordinary precision. These fuses contained a series of gears and escapement mechanisms not dissimilar to those found in a precision pocket watch. When the bomb struck the ground or a building, the impact would activate an arming mechanism, releasing a tightly wound spring. The spring would drive a gear train, which in turn would slowly rotate an escapement wheel at a precisely controlled rate. As the wheel rotated, it would advance a firing pin incrementally closer to a percussion cap. Only after a predetermined number of rotations, corresponding to anywhere from several minutes to 48 hours, depending on the fuse type, would the firing pin finally strike the percussion cap with sufficient force to initiate the chain reaction leading to detonation. The engineering tolerances required were extraordinarily tight. A delay fuse intended to detonate after 12 hours needed to be accurate to within a matter of minutes. Otherwise, it would either explode prematurely, when rescue workers were still in the vicinity, or fail to detonate altogether, rendering the bomb ineffective. This demanded manufacturing precision that was, for the time, exceptional. Each fuse was essentially handmade, assembled by skilled workers who had to ensure that every component fitted perfectly within the others. The escapement mechanism, the heart of the delay system, operated on the same principle as a mechanical clock, controlling the release of stored energy through a series of precisely calibrated teeth and levers. The smallest deviation in the metal components, the slightest misalignment of the gears, could render the entire fuse unreliable. Alternative delay mechanisms were also developed. Chemical-based systems used a corrosive substance that would slowly eat through a thin wire or lead pellet holding back a spring. When the corrosive action finally penetrated the barrier, the spring would release, driving a firing pin into a percussion cap. These chemical fuses were sometimes less reliable than their mechanical counterparts, but they offered advantages in certain circumstances. They could not be influenced by vibration or movement of the bomb after impact. They could be manufactured more quickly and in greater numbers. Experiments were conducted with delays ranging from minutes to 72 hours, though the most commonly used fuses operated on delays of between 4 and 48 hours. The production challenge was immense. British aircraft were dropping tens of thousands of bombs per month on German targets by 1942. The RAF's Bomber Command wanted delayed action fuses fitted to a proportion of these bombs, perhaps 20 to 30% of each raid's load. This meant manufacturing hundreds of thousands of precision fuses every month. Factories in Coventry, Bristol, and other industrial centers operated around the clock, their workers assembling these delicate mechanisms under conditions of strict secrecy. Quality control was rigorous. Defective fuses meant bombs that would not detonate, wasting tonnage that had been expensively delivered to the target, but it also meant occasionally releasing bombs that would detonate prematurely, destroying aircraft as well as German targets. The strategy behind delayed action bombing was devilishly clever. A typical heavy bombing raid on a German city might consist of 500 aircraft, each carrying several tons of bombs. The load would be mixed, some bombs with conventional impact fuses, some with delayed action fuses set for various intervals. As the raid commenced, the conventional bombs would begin detonating immediately, causing fires and structural damage, driving the population into shelters and compelling the emergency services to mobilize. German firemen, rescue workers and civil defense personnel would rush to the affected areas. But as they worked, delayed action bombs, which had lain silent in the rubble throughout the immediate aftermath, would begin to detonate. A bomb delayed by 4 hours would explode as rescue workers were extracting survivors from a collapsed building. A bomb delayed by 12 hours would erupt in a courtyard where emergency supplies had been stored. A bomb delayed by 24 hours might detonate days later, when workers believed the danger had passed and were beginning repair operations. The psychological impact was profound. The German population had developed certain coping mechanisms for conventional bombing raids. They would shelter during the attack, emerge afterwards, and begin recovery. There was a rhythm to it, a structure that allowed people to psychologically compartmentalize the trauma. But delayed action bombs shattered this framework. No one knew when it was safe to emerge. Was the all-clear siren genuine, or would bombs continue to fall hours hence? A street that appeared safe might harbor a device set to detonate at sunset. A building that seemed merely damaged might contain an unexploded bomb waiting in its depths. Recovery workers faced impossible choices: work quickly and risk detonation, or work slowly and allow the damage to accumulate. The German response was initially chaotic. Air defense authorities had no experience with this type of bombing. They lacked protocols for identifying and neutralizing delayed action bombs. Some were destroyed in place, carefully excavated and deactivated by specialists, a process that was slow, dangerous, and consumed enormous resources. Others remained hidden in the rubble, their presence only confirmed when they finally detonated, often destroying additional structures or injuring workers. The Reich had to establish entirely new organizations to deal with the threat. Bomb disposal units were expanded, and specialized training programs were established. Gestapo units were deployed to prevent sabotage of the removal process. But nothing could entirely eliminate the risk. Every delayed action bomb represented uncertainty, and uncertainty was precisely what Britain sought to inject into German civil defense. In the Ruhr Valley, where German industrial capacity was concentrated, the effect was particularly pronounced. The Ruhr Campaign of 1943, conducted over 16 consecutive nights in May and June, employed delayed action bombs extensively. British bombers dropped not hundreds of tons of explosives, but thousands, and a significant portion carried delayed action fuses. The German authorities lost control of the situation. Factories could not operate because workers could not guarantee safe passage to work. Repair crews could not complete their work because new explosions would disrupt operations. Entire sections of cities remained cordoned off for weeks, their infrastructure unusable, their population displaced. German records from the period reveal the mounting frustration. Military commanders demanded that the bombing be stopped. Civil authorities pleaded for resources. The Führer himself was reportedly enraged by the vulnerability revealed. It is important to acknowledge the limitations of historical record regarding delayed action bombing. Some German documents were destroyed during the war or in its aftermath. Some statistics regarding the effectiveness of the campaign remain classified by modern governments. Estimates of casualty figures vary depending on the source and the methodology used. What can be stated with confidence is this: delayed action bombs changed the nature of the air war over Germany. They transformed bombing from a straightforward trade in destruction into a campaign designed to disrupt, paralyze, and psychologically devastate. If you are finding this interesting, a quick subscribe helps more than you know. The German Luftwaffe had experimented with various bombing innovations, but they had not developed anything equivalent to the British delayed action bomb system. The Germans did produce anti-shipping bombs and armor-piercing bombs for specific tactical purposes. They developed guided weapons and other exotic devices, but they lacked the industrial base to produce delayed action fuses in the quantities required for a sustained bombing campaign. German bomb design tended toward simplicity and robustness rather than mechanical complexity. Their fuses were, by and large, designed for immediate detonation. When the Luftwaffe attempted to copy British delayed action bomb designs, intelligence about which had inevitably reached German planners through various channels, they struggled with the manufacturing precision required. Their factories, already stretched to capacity by the demands of the war, could not reliably produce the necessary components. By the time German delayed action bombs appeared in any quantity, the air war over Germany was effectively lost. The Luftwaffe was no longer in a position to deliver them in sufficient numbers to constitute a strategic threat. The Americans, meanwhile, developed their own approaches to bombing strategy, though their methods differed somewhat from the British emphasis on delayed action weapons. American bombing doctrine favored daylight raids with high-altitude precision bombing, attempting to strike specific military and industrial targets rather than engaging in the area bombing campaign that characterized British operations. The Americans did employ some delayed action bombs, but not as a primary strategic tool. American bombing philosophy held that accuracy mattered more than the prolonged disruption created by delayed action fuses. Yet, even the Americans came to recognize the value of what the British had discovered. By 1944, delayed action bombs were being incorporated into American bombing loads, particularly in raids aimed at transportation infrastructure, where the prolonged disruption they caused could be particularly valuable. The impact of delayed action bombs extended beyond the immediate tactical effects. The campaign to incorporate them into British bombing operations required an enormous research and manufacturing effort. Precision fuse production became a critical part of the war economy, employing thousands of workers and consuming significant quantities of raw materials. The success of the campaign also validated a particular approach to air warfare, the idea that bombing could be designed not merely to destroy but to disrupt, paralyze, and demoralize. This philosophy would influence air power thinking for decades after the war. Military theorists would study the delayed action bombing campaign as an example of how understanding the enemy's vulnerabilities. In this case, the reliance on rapid recovery from bombing damage could lead to innovations that dramatically increased the effectiveness of bombing campaigns. In terms of historical impact, the delayed action bomb campaign made a measurable contribution to the eventual defeat of Nazi Germany. Some estimates suggest that delayed action bombs accounted for perhaps 20 to 30% of the total disruption caused by British bombing operations in 1943 and 1944, despite representing only a minority of the total tonnage dropped. The campaign forced Germany to divert enormous resources to bomb disposal, civil defense reorganization, and repair operations. It accelerated the evacuation of civilian populations from German cities, further disrupting the social fabric of German society. It contributed to the sense of fear and uncertainty that characterized daily life in bombed German cities. And, crucially, it provided a measure of strategic justification for the area bombing campaign itself. The argument being that the effects of bombing extended beyond mere destruction of buildings to include the psychological and disruptive effects created by weapons like the delayed action bomb. Today, the engineering behind delayed action bomb fuses can be viewed in various museums and archives. The Imperial War Museum in London holds examples of Type 17 and Type 47 fuses, along with technical drawings and manufacturing records. The Smithsonian Institution in the United States possesses examples of both British and German fuses, allowing for direct comparison. These mechanical devices, seemingly simple by modern standards, represent a crucial innovation in the history of warfare. They demonstrate the principle that innovation in warfare is not always about creating entirely new weapons, but sometimes about subtly modifying existing ones in ways that exploit vulnerabilities in the enemy's defenses and expectations. The delayed action bomb was not the most destructive weapon of the Second World War. It did not kill more people than conventional bombs or fire raids. It did not destroy more industrial capacity than precision-guided weapons eventually would. But it represented something conceptually important. the realization that time could be weaponized, that uncertainty could be more valuable than raw destructive power, and that innovation in warfare often came from understanding not just how to hit a target, but how to exploit the human and organizational vulnerabilities that surrounded that target. It was a British innovation born of necessity and desperation, developed by engineers and technicians whose names remain largely unknown to history, and deployed on a scale that eventually contributed to the collapse of German resistance. In the rubble of Cologne and Hamburg, in the terrified faces of German rescue workers, in the desperate scramble of military planners trying to respond to a threat they could not fully comprehend, the delayed action bomb demonstrated its terrible efficacy. We began in the darkness over Cologne, with searchlights and sirens, with the knowledge that something was falling from the sky. We understood, in those opening moments, only that bombs were falling, that danger was imminent, that the familiar horrors of air raid were about to unfold. But we did not understand, and the Germans did not understand, that the real danger lay not in what was exploding in that moment, but in what would continue to explode in the hours and days to come. The delayed action bomb turned bombing from an event into a process, from a moment of violence into an extended campaign of terror and disruption. It represented the capacity of human ingenuity to transform the familiar into something far more sinister. And in doing so, it fundamentally changed not just the conduct of the air war over Germany, but the entire nature of strategic bombing itself.